Numbers, Class 10. The topic for today is rational numbers and their decimal expansion. We are picking up a theorem. The statement goes, let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-prime and the prime factorization of q is of the form 2 raised to power n into 5 raised to power m, where m and n are non-negative integers. This is theorem 1.5 from your NCERT. Let us understand this with the help of an example. Suppose we have a rational number 0.33. Now see, we know this is a terminating decimal, and if I write it in the form of a rational number in p by q form, it becomes 33 by 100. We know why it became 100, because after decimal there are two digits which are repeating. There are two digits after the decimal, therefore it is 33 upon 100. Further, it is 33. Now, how can this 100 be written in prime factorization form? 100 we know is actually 10 square, and 10 has the factors. What are the factors of 10? It's 2 and 5, and its common part 2 comes as such, and this is 33 upon 2 raised to power 2 into 5 raised to power 2. And here goes the result, which says whenever any decimal, whenever there is a rational number whose decimal expansion terminates, we know this is a rational number because its decimal expansion has terminated. Then it can be expressed in p by q form, where p and q are co-primes. 33 by 100, they are co-primes. They don't have any other common factor other than 1. And the prime factorization of q is of the form 2 raised to power m and 5 raised to power n, the product. So what are m and n here? The value of m and n is actually 2 in this case, and they are non-negative integers. Non-negative integers indicates they should be positive integers. Our next theorem is, this is theorem 1.6. It says, let x equals to p by q be a rational number such that the prime factorization of q is of the form 2 raised to power n into 5 raised to power m, where m and n are non-negative integers. Then x has a decimal expansion which terminates. This theorem is actually converse of what we did in previous case. So in the previous case, we have seen the number, the rational number where the base was having the power of 10 terminated. That was a terminating decimal. Now let's take another rational number. It's 1 by 4. It can be written as 1 upon 2 square. Now if we want to change it into the base of power of 10, what can we do? We know 2 square, and if 5 square comes in the denominator, this would become 10 square, but the number in totality remains, it should be balanced. So if 5 square is written in denominator, 5 square should be written in numerator as well. Now 5 square upon 10 square, because 2 into 5 makes it 10 and the power square comes as such. When you further simplify, this is 25 by 100, which is 0.25. Let's pick another example. If the number is 7 by 80, we know it's a rational number. It can be written as, let me write the prime factorization of denominator. 80 can be written as 2 raised to power 4 into 5. And if we want to express this number in the decimal form, the easiest way would be make the base with the power 10. Now 2 has already got the power 4, 5 is just having power 1. If I write 5 cube in the denominator, to balance this whole number, 5 raised to power 3 or 5 cube should be written in the numerator as well. Now let's see what this number would look like. Numerator would be 7 into 5 cube and denominator becomes 2 raised to power 4 into 5 raised to power 4. And look at the next step. 7 into 5 cube is 125. Denominator is 10 raised to power 4. Product of 7 and 125 is 875. And denominator would be 10,000. And further, when you simplify this is 0.0875.